Hi, welcome to lecture 18 of Quantum Physics for Non-Physicists. Today is the 12th of November. And today we're going to try to bring together everything we've done in the previous lectures. So we'll do a recap of the this uncertainty about evolutions, and then we'll see how in particular we can apply this to measurements and how we can model measurements as quantum channels. We'll start with that. And as promised, we'll do half an hour more, which means we'll do 45 minutes. And we take a break of 15 minutes at 12:30, and then I'll do another half an hour. And obviously, you don't have to watch everything live. I'll update the video later. Okay, good. So the daily analogy, bear with me because it takes a while to explain. So I'm reading this book now, and I think it's not spoilers to say what I'm saying because it's established very early on in the book. So this is about two time travel agents, red and blue, who work for different agencies, and they always trying to sabotage each other's missions. So they go to a very different setting in space and time, and one is trying to steer the timeline in a certain direction, and then she finds out that the other one has already predicted that she'll do this and left her a message. Okay, so the whole book, it's always one of them is trying to do something, finds a message from the other one that's, I don't know, ingrained, for example, on the rings of a tree or in the entrails of a seal, or I don't know, it's some bits in some computer. So she reads the message and then she destroys it. Okay, so she burns it, or she eats whatever animal it had been encoded on, or I don't know, she makes a table out of a tree, something like this. And then after this, there comes this mysterious character, the seeker, who goes and gets all the remains, like all the ashes from the fire in which this message was burned, and slowly puts them all together and manages to read the message again. Okay, so what's the analogy here? Is that you have an operation that seems to be irreversible when you look at it locally. So you burn the message, surely it's destroyed. But if you have access to all the degrees of freedom, you can globally find a reversible version of this and revert it, which is what this seeker does, right? Of course, it's completely unrealistic. That's not the point. It's a fairy tale. But it's this idea that we saw in the previous lecture that even if you have an irreversible operation like a map, you can always see it as a reversible operation, the unitary acting on a larger space, followed by the partial trace, which is essentially meaning we forget some information. So that's how it's applied in this book. Regarding to housekeeping, so I'm continuing to go through your feedback, and it's been very, very useful. And because everyone tells me that there's lots of terms I don't explain, but again, I don't know what terms these are. I created a glossary, so this is on Moodle, and it's also on your email, probably around now, should have received it, or will so in the next few minutes. So I just created a Google Doc where you can write down any terms you don't understand, or you're not familiar with, or you're not sure. And then Nuri and I will go through it and just fill out the table. And I'll also explain it in a lecture after which terms these were. Right? In real life, I hope you'd ask me right away if I mentioned something. So in the lecture, you can also ask me right away if I mentioned something you don't know. Okay. So let's recap what we've been doing in the previous lectures. So we talked about quantum channels, which means we have some uncertainty about the global operation, about the operation that we are performing on a state. So this is some kind of evolution, and to be physical, you must map density matrices to density matrices, meaning valid quantum states to valid quantum states. And so some examples could be, for example, I have an optical fiber, and I send some photons through it with some internal degree of freedom that I care about. So this could be, for example, the polarization of a photon. Don't worry too much about what it means. It just means that some qubits inside this particle. Okay. So we send it through it, but because there's always, I mean, optical fibers are very clean, but there's still always some noise, some interaction with the environment, the longer the fiber is. So the state that you get at the end is not exactly the state you put in. Okay. And this kind of evolution can be modeled by a quantum channel. Another example could be just a memory where you meant to store some state, but this memory is also subject to, I don't know, an environment that's at some temperature. That means that air particles are bouncing against it. So in the end, the state that you recover at the end will not be exactly the initial state. Okay, so an example could be a solid state hard drive, for example. Okay, where what you're storing are in fact quantum states, highly redundant, of course, but quantum states. So if you leave it there for a long time, if you play with the magnet next to your computer, etc., then you know that the memory can be damaged, for example. Right? And a quantum channel, meaning an irreversible evolution, is something that can model this kind of things. The other example, as we saw before, is something that is globally, for example, there's Alice and Bob, and Bob does some operation, but Alice doesn't have access to it, for example. So we know that there's a global unitary operation, but we don't know what the local impact is. So we'll see this in much more detail now. Again, so let's just recap. We saw that there's two representations of this. One is the cross representation that's not unique. So, which means you can represent a map as the sum of these operators. And let's just go a bit into more detail of what these operators are. So remember, maps in general can transform from some system A to a system B. They don't necessarily need to have the same dimension. Okay, so for example, you could say, I want to compress an image. So I want to start with a very large number of bits and end up with a very small number of bits. Okay, so there exists quantum equivalents to this kind of things. So in this case, the final space D would be smaller than the final space A. Okay, so what are the dimensions of these objects? So suppose that row A has dimension dA. So it's a square matrix, for example, in this case, 4 by 4. And so 2 qubits, and we want to end up with 1 qubit. So dimension of B is going to be 2. Okay, so we want to end up with a 2 by 2 matrix. So by the way that you put there, so here's the EK, and there's the EK dagger. And the way matrix multiplication works is that, so to get this element here, you multiply 1, 2, 3, 4 by 1, 2, 3, 4, right? To get this element here, 1, 2, 3, 4, 1, 2, 3, 4, there. And then do the same on this side. So meaning that if this is a matrix 4 by 4 and we want to end up with a matrix that's 2 by 2, then this one will be 2 by 4. Okay. So this is dB is the number of rows and dA is the number of columns of this matrix. So this is just to give you an idea of what kind of objects these are, and to be a Krauss decomposition when they need to sum up to the identity in this form. And we saw this is a necessary condition in order to be able to represent them in this time spring dilation form. And this is precisely this idea that what we have is actually unitary acting on a larger system. So here's our initial state row A. We'll end up with some map applied to row A. But if you look at the big picture, what we have is we can have some ancilla or some environment in some state. We apply some global unitary to it, and then we just trace out the environment again. So that's this way of seeing it. And then we can just call this whole thing an isometry on row A. What's the difference between a unitary and the isometry? Essentially, the unitary is a square matrix and the isometry is a rectangular matrix. Meaning for the unitary, it's invertible, right? And it's square, which means goes from one system to itself, or to a system of the same dimensions at least. Whereas the isometry, well, it's also invertible, but depending on the order in which you put V and V dagger, you get either the identity in the origin space or the identity in the final space, right? Initial or final space. So this corresponds to kind of dilation or compression to different subsystems, but in a way that's reversible. Okay. And for all this, for this to be a unitary, then we need to have these dimensions to match up, which means it's dimensions of A and B together. So they multiply when you have a tensor product. The word product should be a hint. So these two dimensions, when they multiply, they should be the same as these two dimensions multiplied. Okay, so this is system E, A, E, E prime. And finally, we saw how to translate between one and the other. So we'll give an example of this, don't worry. We saw how to translate between one and the other representation. So we saw that we can, so this is the Stein spring dilation representation. This is the Krauss operator representation, and having this kind of isometry actually achieves this translation between the two. Okay, good, and we kind of prove that this works out. Right, there's many things that we're not covering here. For example, the fact that all maps, all valid maps can be written in these two forms and vice versa. That these two representations really are complete to represent all quantum channels. But we'll not get into this. This is studied, for example, in quantum information theory, if you want to take in the next fall semester. Okay, so let's continue. And today we'll mostly see an example throughout the whole lecture. Okay, and it's going to be a very simple example that will give us more work than you might predict. So we want to have a global operation that is reversible. Global operation. And we go to our go-to operation, which is the C naught. Okay. So we have row A. Here we have some 0 on E. And then we just have a C naught between the two. Okay, so this is B is the same as A. So here end up with E of A. And here E prime is the same as E. And eventually we'll trace it out so that we want to see from this global unitary, what is the map that we end up with. And this will be very useful because this very simple example, as we discussed again and again, is a model for quantum measurements, right? You could think of A being the system you want to measure and E being the pointer system. Yeah? So we'll see now how it works in this discrete case, and then we'll see the continuous case. Very good. So first, let's just see what U looks like. So U goes from AE to B E prime, where B is the same as A and E prime is the same as A. So this was a C naught, which if you remember is represented like this, which is 0, 0 times the identity plus 1, 1 times X. Right, so essentially checks if the first qubit is 0, it flips the second. Sorry, it does nothing, but if the first qubit is 1, then it flips the second. Right. Okay, and what is row A? Well, it could be any density matrix at this point, right? So let's just say it's sum over I and J going from 0 to 1, Cij, Ij. And let's just represent it in matrix form. So the way to do this is to think in the following way. If you're multiplying by something else in front of it, then it becomes kind of clear that rows correspond to different kets and columns correspond to different brush. So we get here C00, C11, and here C01 and C10. Okay, that's kind of the way to do it. Okay, what's row AE? Well, it's just the initial state. It's just row A tensor 0, 0, and E. So that's the sum on I and J, again from 0 to 1, Cij, ij on A, tensor 0, 0 on E. And we can represent it like this, or we could represent all the cats together and all the bras together. But let's just see what matrix this is. Let me tidy things a little bit. More space here. So this is going to be a 4x4 matrix. We don't have space for it here. Let's do it to the next page. Okay. So again, we're going to draw a very big matrix, and let's just think about this a little. So here is going to be corresponding to 0, 0, 0, 1, 1, 0, 1, 1. Now here, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so let me just write this in the other form. Cij I0, J0. Okay, where this is A and this is E. A. Okay, so this means here we have 0, 0. Then everywhere where there's a 1 in the second system is going to be 0. So it can go like this. Chuk, 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 chuk. Sorry, let's just adjust this a little bit. There you go. Everywhere where there's a 1 on this row, this is also zeros. 0, 0. Okay, so now we just have this place to put everything that's left. This is going to be C11, and this is C01 and C10. Okay. Good. That's what we've got. So if you take the original matrix, multiplying with, tensoring it with 0 on the other side, it just kind of spread out the non-zero terms. Okay. So now we need to do first U diagram. And in this case, it's very convenient that U equals U dagger, because the complex, I mean, if you transpose this, you get exactly the same matrix, right? And the conjugate doesn't do anything. Okay, so now we have to multiply these two matrices. And maybe I just show you the result. Okay. So the result is going to be that you have the C00 here, and then we have 0, 0, C11, 0, 0, C10, 0, 0. Oh, sorry. This was 0, 1, and this is C11. How did I do it? I really just multiply this matrix, that matrix with this, and then U again. So what is this? So this is C00, and that term here. This corresponds to having 0, 0, 0, 0 plus, switch here, C01, and this term here corresponds to what? Corresponds to 1, 1, 0, 0. So plus C10, and now it's going to be the opposite. Plus C11, 1, 1, 1, 1. Okay. Can we simplify this? Yes, we can, because it's a C0. It did what we expected it to do. Whatever we have on the first system, we have in the second, right? What's in the first system, it's on the second. What's in the first is in the second, and so on. So we can simplify this to sum over I and j, Cij, I, j, j, which we can rewrite if you prefer. It could be easier for later. In fact, it's going to be easier. Cij, ij on, we call this B system now, but it's the same as A, and ij. This is what? Okay. So how do we get the map? We don't have the map yet. So the whole map on row A, it's going to be trace over E prime of this thing, right? Of U, row A tensor 0, 0 on E, U dagger. And this part we've already done. Okay, so now we need to do the partial trace. Okay, so what is this? Trace over tag of what matrix? This one that we just saw, Cij, ij on A, tensor ij on E prime. Okay, so, but what's the partial trace? Well, the partial trace is just the sum over basis elements of, oh, sorry, this we call this B now, right? It doesn't matter, A is the same as B. Identity on B, tensor L on E prime. Now comes that thing again. Identity on B, tensor L on E prime. Okay, and let's just copy the thing. Oh, let's not copy it. Let's just say it's the same thing. And let's just rewrite this thing. So you have sum over L, sum over I and J. And now what we have, so nothing happens to these terms because they're acted with the identity. So they survive, and these terms kind of get pinched by the brown on one side and the cat on the other side. So let me just write it down. Cij, then f I, j over b, and then what we have is this inner product L and JL, right? Now, these are numbers, which is delta of minus E, delta of J minus L, right? Okay, so at the end of the day, what we have is a sum over I, Cii, II on B, which in matrix form is what? It's just C00, C11, 0, 0. Okay. So let's just, by the way, there's a trick. Okay. So if you do the trace over E prime of a big matrix, let's get the matrix again. If you have a 2-qubit matrix and you take the partial trace over the second system, then very conveniently, the terms are given by sums of a kind of partial diagonals. I'll tell you what this means in a moment. I took a 1 away. So this is going to be a smaller matrix where this gives you the first element, gives you this element here. The sum of this term and that term gives you the first element. So that's C00. This diagonal gives you this term here. The sum of this little diagonal gives you that, so that's a 0. Let's go on. This diagonal gives you this term, that's also going to be 0. And one more color. This diagonal sum gives that. Is the C naught applied column-wise? Someone is asking. I'm not sure what you mean. So I really just multiplied. Take this matrix and multiply it by this one. So I have it here in the draft somewhere. Let me try to find it for you. I decided not to do it. So this is how you do it, right? Is the C, here's the C naught, here's the matrix, here's the C naught again. So you just do, to get the first element, so I'm just multiplying these two matrices, right? Is this times this, meaning this element times this, plus this element times that, tac, tac, plus tac, tac. Only one term survives. To get this one, it's this row times this column. They're all zeros, so you get a 0. To get this element is this row times this column. So 1 gets multiplied by this, plus zeros times that. So you get this term. And so on. You do this for all rows and all columns. And then you do it again for the second element. I don't know if this answers your question. Okay. You're confused on the intuition. It's really just, okay. You get the idea that, let me just write it here somewhere. We get the idea that rho evolves as U, rho, U dagger. Right. Right. So for example, you could have rho being this, right? So then when you evolve it, then you get rho. If rho is a pure state, right? Then you get rho going to C naught applied on psi, C naught complex conjugate, right? So this is the final state here, and this is the final state there. And now if you have rho being a sum over i's of this, then you just have here the sum over i's, again in the same way, right? Okay, right. But this is if we already knew, this is if you already knew the eigenbasis of rho, so we know its decomposition into pure states in that way. So like pi here. But we just get a matrix, so this would be a matrix that's already diagonalized, right? That looks like P0, P1, P2, P3. Okay, this would be rho, where this basis corresponds to yeah, phi 0, phi 1, and so on. Sorry, these are brass. No, these are cats. These are cats. Okay, right? But if you have a matrix where you don't know, you have some non-diagonal elements, okay, then the only difference is that here you have ij, pij. So you have elements here, pij, so we have the I here and the j there, which is what we did now. Okay. Okay, so let's continue. Let me erase this just so we have a clean page to come to. Okay. Right, and this is really just a trick to do the partial trace. In the very specific case, that happens a lot, where you have two qubits and you trace out the second, you can just look at this diagonal, sum them up, and you get the little thing. But really, this is a trick. Okay, so what did we learn here? So we start with our initial state, shows sum ij, cij, ij, which was this thing, 0, 1, 0, C1, 1, right? And now we ended up with only the diagonal terms, right? So what the map did was kind of what is called in quantum information, they call it kind of pinching the matrix, so getting rid of the off-diagonal terms, right? Pinching just the diagonal. Okay, so we got rid of the off-diagonal terms, and now we can think about, well, if you want to have the cross representation of the map, so we want to have this thing expressed in terms of EK, or a EK dagger. So what could be good examples for the EK? And now I'll give you one solution because I already know it. So let's go get Sherlock. So again, this means it's a trick in the sense that it's a solution that I already know, and I don't know how easy it is to look at it and just see immediately what it is. But so let's try 0, 0 being just a projector into 0, okay, which is this matrix 1, 0, 0, 0. And E1 being the projector into 1, which is 0, 0, 1. 0, 1. Okay. Okay. So first of all, does this work? What's the normalization condition? This should be the sum over K over AK, should be the identity of AK dagger K. But this is what? This is 0, 0 multiplied by itself, because the transpose is the same, plus 1, 1, 1, 1. Okay. And this here is an inner product that's 1. This is an inner product that's 1. So overall, we get to 0, 0 plus 1, 1, right? So that's the identity. It works. Okay. And now let's just see that the map really works as we wanted. So E of rho A. So now let's say it's the sum over K, EK rho A, EK dagger for an arbitrary rho A. Okay, let's do it. Because it's just a qubit, we can do it in a matrix form, but you can also do it in direct notation and get the same. So 0, 0, 0. And here's C0, 0, C0, 1, C1, 0, C1, 1, 1, 0, 0, 0, plus the same thing with the other operators. So 0, 1. Yeah. But what survives here in the first one, so this term survives, and all the other terms are going to be 0. Okay. And here again, this term will survive, and all the other terms are going to be 0. So if you want, you can multiply the matrices at home and see that this is indeed the case. But what we get is this plus 0, 0, 0, C1, 1, which is the matrix that we wanted. Right? So this also works. Okay. So now I told you that the C naught is kind of like a measurement from the outside view, right? We saw several examples where maps that act like C naughts in discrete and continuous systems can be used like a measurement. And the local action is this kind of pinching off of the diagonal terms of the off-diagonal terms of the density matrix. So now let's see an even more special case. Okay, so we see a sub-example. So it's still the same example, but now let's do a concrete state, initial state. So let's say rho A is a pure state in this case, okay? Where psi is some alpha 0 plus beta 1. Okay, so it's a superposition of 0 and 1 with coefficients alpha and beta. So this is what is the density matrix like? So it's going to be alpha 0 plus beta 1, alpha star 0 plus beta star 1, because they could be complex numbers, right? So this is alpha 0, 0 plus alpha beta star 0, 1 plus alpha star beta, that's beta 1, 0 plus, sorry, this should be beta alpha square, beta square 1, 1. Okay. So what's the density matrix that corresponds to this? In matrix form, that's alpha squared here, alpha tac tac tac, alpha tac 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 beta, and here beta square, right? And this is a pure state, so in particular, you can check that rho square is the same as rho. Okay, it's not obvious by looking at the matrix in this form, but if you look at this state, you just multiply this by itself and you get an inner product that's 1. So you get again the same matrix at the same state. Okay, so in a pure state, if it's a superposition, then we have these off-diagonal terms that are relevant. And when we apply the map, E of rho A, then we get only the diagonal terms. Okay. And this is what this corresponds to alpha squared 0, 0 plus beta squared 1, 1. Okay. So we kind of got rid of these terms. Okay, so this measurement, if you look only at the local action, it's like this pinching. But we can say a bit more if you're thinking about what's the physical intuition behind it. Okay. So again, if you look at this E of rho A, this thing that we just saw, we have this, right? And now, if you remember, what was this? What were these numbers, these coefficients? Well, this were, if we had the initial state, right? Our beautiful pure state. Let me draw something around it so don't forget it. When we thought about, oh, what happens if I measure this in the 0, 1 basis, we saw that the probabilities of getting 0 were alpha square, and the probability of getting 1 was beta square, right? Modular square. So this is actually the probability of getting 0 when measuring the initial state. And this was the probability of getting 1 when measuring the initial state, right? Which is what? Well, which was given by the trace of the projector into 0 times rho, okay, which is 0, 0, and rho was, as you know, psi, but let's just put 0. Let's just put rho here, okay. Which in this case, it's exactly the same as this EK rho, okay. And it's the same as EK rho, EK dagger. Okay, so this is the trace of 1, 1 rho. Okay, so this means that we can write this final state after this map as probability of getting 0 on our initial state and 0, 0 plus probability of getting 1 in our initial state times 1, 1. But what is 0, 0? We can also look at 0, 0 as, well, we saw that if you get outcome 0, then the post-measurement state is 0, right? If you look at it again, it's going to be 0 again. It's this thing that some people call the collapse of the wave function. So this is like the post-measurement state. If we measure 0. And this is again the post-measurement state if we measure 1. Okay. So what we have here, so we have that this map applied to the initial state, what we have is the probability of measuring 0 versus what happens if we measure 0, plus the probability of measuring 1 times what happens if you measure 1. Okay. Which is a way of looking at what the post-measurement state is from the perspective of someone who doesn't know the outcome. Okay. So to give you maybe a classical analogy, so suppose that the measurement is trying to check if you won the lottery or did not win the lottery. Okay. And someone from the outside, you check it, but someone from the outside who doesn't know the result wants to describe your state, right? So they say, well, your state, the state of your wallet, is probability that you didn't win versus 0 money, plus probability that you won versus a lot of money. Okay, so that's the idea. So you can look at this as being a description of what's happened to our system from the perspective of someone who doesn't know what the outcome was. Okay, who knows that there was a measurement. I know that you checked the lottery, but I don't know what the outcome was. So I'll just write this here, and then we can go for a break. So epsilon of rho A represents the post-measurement state from the perspective of someone who doesn't know the outcome. What I mean by this is it's a probabilistic mixture of the two outcomes. Right? Okay. So again, just to go back to the big picture. So we had like rho A and the 0 on the pointer. We applied this unitary that in our case was the C naught. And of course, the final state is correlated, but if we trace out this environment, then you end up with a map, okay? Which means that we can represent measurements that we knew how to represent as unitary operations on a global system as maps, as quantum channels. And in the case of this measurement, very simple measurement that we saw, a projective measurement, you saw that the cross operators actually, where are the cross operators? Yes, here they are. The cross operators corresponded to the measurement projectors precisely, right? In this case. So I'll just write represent, I'll just call projective measurements. As maps. So meaning quantum channels. I'll just write quantum channels. Where so is a rho sum over k ek rho ek dagger, and in this case ek corresponds to the projector into outcome k. So okay. So this we can generalize for the case where like these coarse-grained cases that we saw before. Okay, we'll take 15-minute break, and I'll see you again at 1:45. And what we'll do in the next half an hour is just to kind of prepare for what happens if we have a softer measurement like these continuous measurements where the pointer is a Gaussian position of a particle. Okay, so I'll stop now and see you in 15 minutes. Let's continue. So just to summarize, we saw that at least for the simple case of the C0, it looks like we can represent this measurement as a map, as a quantum channel, where the cross operators correspond to the measurement projectors into different outcomes. We did not prove the general case, and I think we will not prove the general case. This is again done in quantum information theory. But you might be wondering, what about continuous pointers, right? Because before we spent a lot of time talking about the pointer like being a particle in a line that later measures the position of. So we can do it. So remember what we saw in one of the first quantum analogies. If you can solve discrete systems, you can solve continuous systems. Okay, you just have to find the right parallels. So then let's do this. So first, we'll just see what's the equivalent of the C0, which we saw before, and we'll just see under what conditions we get exactly the same kind of map. Okay, so let's see. Let's start. So we take the H global being in two systems, HA tensor HX, where X is a continuous one, and A, we don't care, it could be continuous or discrete. But then we have an observable, a discrete observable on A. On HA, okay? Which means we can write MA as some sum AI. So this is a very, very simple case, okay, where it's just a measurement into some basis. So more generally, you could have here some pi I, projector pi I. But for now, we keep this very, very simple case. So we take A. In this example, A is even a discrete system. And X is continuous. It also works if A is discrete. And then we saw in the past that the interaction Hamiltonian, one interaction Hamiltonian that worked for this was to take a H to be the observable on A, symmetrics tensor, the momentum operator on X, right? And then we saw that from here, we got that the evolution was given by E minus I T over H bar. Remember this? MA tensor PX, right? And then we saw this special case for the initial state, which is just saying the initial state is a pure state, okay? So we're not going to do for now the initial state being a general density matrix, just because it would be more complicated, and we would not be gaining much more insight from it. So let's see. Let's say the initial state on A and X is any state on A, which you can expand in the basis of our observable. So this CI is not the same as that. So we just expand it here, and phi 0 on X, where this is a wave function, it can be represented by a wave function, right? Phi 0 of X. Okay. And it could be this special example where it's kind of a Gaussian, right? Something like this. Okay, so this is just initial state. So we saw also how it evolves under this evolution. So we just do it. And for now, we're just repeating what we did before. So the evolution. Oh, was I using light blue? Oh, let's be consistent. Okay. So then the evolution U of t initial state. So we saw that it acted as this. This we've done a few lectures ago. E minus IT. Because, so this operator MA acted here and just returned the exponential of the eigenvalue, right? Because these are the eigenstates of that operator. Okay, so there they are, the eigenstates of the operator, and then E on X, acting on phi 0 on X, right? Okay, and then we also saw that this is the modular momentum operator, so all it does is take the wave function of this and shift it to the left or to the right according to this coefficients here. So we saw that this was sum over I, Ci, Ia, tensor, dx, phi 0 of X minus t AI. And I will just call this thing here. So this minus could be also a plus. I don't remember which way it goes. So it's either minus or plus, but that's not too important for what we want to do. Okay, just call this the function phi I. So let's look at an example of what we did. So we saw. Let's look first at the simple example where we'll be able to find a direct analogy. Okay. So suppose this was the initial wave function. Very nice, kind of Gaussian, but that we really cut off. So what we have, the y-axis is the wave function square. This is x. Okay. So this would be the wave function for the initial state phi 0. Okay, this initial state here, and this whole area kind of gives us 1-ish, and then you'd get as the final state. So this gets kind of shifted, and you get these little bumps, which are, for example, this could be phi 1, and maybe this here is phi 2. If A has 2 outcomes, for example, we're measuring a qubit, so we have 2 possible outcomes, and this, the weight of this component would be psi 1 squared, and the weight of this component would be psi 2 squared. Okay. But let's take now, so this is what this operator did. So it just kind of shifted the wave function by some amount So this here is like TA1, and this is T2, right? Okay. Good. So in this particular case, if you look at this region here, okay, because of the way we chose the pointer, etc., there's no overlap between the two possible outcomes. So this means what? If you have what does no overlap mean? In practice, it means this equals 0. Yep. So let's see what happens in this case when let's see if we can recover what the map was on the system A. So right, this is us looking at what happens to the pointer in the case where for outcome 1 and outcome 2, and what we get is a superposition of these two wave functions, correlated, of course, with having the outcome I on system A. So we want to see what happens to system A. So let's call this final state. Okay. So the final state was on A and X was sum over I, Ci, I on A, and this Psi I on 0, right? That's what we call them. Call them Psi I on X, sorry, with this condition that they're non-overlapping. So on X. So if we take the density matrix on A and X, well, this is just the final state times itself. And if you do that thing, you get sum over I and J, Ci, Cj star, Ij on A, tensor Psi I on Psi J on X, right? And now, in order to get the action of the map, so this was this was kind of U of T initial state U of T dagger. So instead of first getting this density matrix and then doing this multiplication by two matrices, because it was a pure state, we just evolved this, found out what this was, that's this final state, and then we computed the density matrix. Okay, so this is rho final. But now we know that the map applied to the rho initial is going to be trace over our X of this thing, of rho final. Okay, because this is trace over X of the global evolution on the initial state. Because this initial state already has the system and its environment, which is the pointer. Okay. So what's the partial trace? Just like before, this is going to be nothing happening on A, tensor X happening on B, go final. Okay, and now the same thing, nothing happening on A and X happening on B, right? The only on X. Yeah, so the only thing that changed was that instead of a sum for the, we have an integral, right? And this goes from minus infinity to plus infinity. Okay. So let's write what this is. So this is, don't worry, it will actually be quite fine. Okay. First I write everything and then we simplify it. Now I put here the states, sum on Ij, Ci, Cj star, Ij, A, tensor psi I psi j. Oop, this is on X. J on X times again identity on A tensor. Right? Okay. Very good. So now let's just simplify it. So what's happening on system A? Not much is happening on system A, right? This identity acts there, does nothing, and this identity acts there and does nothing. Okay, so this is all left undone, and then this X acts there and this X acts there. Okay. So we get sum over, we can take the sum outside. I, C, J, check, check, check. We get I's and J's on A. These don't depend on anything. And then we have dx. And now here it is X psi I. And whoop, psi J X, right? Okay, and now we're going to do, these are just numbers, right? These two things, they are numbers. So we can swap the order of them. Okay, so this is a number, belongs to C. This is a number, belongs to C. So we can swap the order of the two. Okay, let's do that. So where were we? Epsilon rho A was the sum over Aj, Ci, Cj star, Ij. And now came this sum dx of, we just swap the order. So we just put psi j x. No, sorry, this is wrong. Up. Psi j x, and here x psi I. Okay. Now, well, these terms do not depend on. So remember this, although the whole thing is a number, this is still a row vector multiplied by a column vector, right? So this is something like a row, and this is something like a column. So this one does not depend on X, and this does not depend on X, so we can take it outside outside the integral. Okay. So we have Ij, Ci, Cj, check, 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 Ij. And now what we have here is psi j, sum dx, xx, phi I, right? But this is just the identity on X, right? If this was a discrete system, this would correspond to this matrix. It's really just the identity. So we can get rid of it without making any problem. So we have, okay, sum over j, Ij, Ci, Cj star, Ij, and then there's this coefficient that becomes say j psi I. Okay, good. So now we go back to our special case that we saw. Well, in this case, right, there's no overlap between these two kits. So this is 0, right? So we'll just use this. Special case of Ji, this being delta Ij. Okay, so in this case, then we have all the terms where I is different to j disappear. So we get just the sum over I of Ci, Ci star, I, which is sum over I of ci squared I, okay, which is exactly what we had for the discrete case where the pointer was discrete, right? So again, it's like we start with maybe I should just draw what the original state is. So let me see. Maybe here we can make some space to just write what the state was. If I made the density matrix here, this would be only phi 0 on x, and on A, you have all the cross diagonal terms. So ij, ci, cj star, I, j, a, right? So if I took this state and I just wrote, so this should be the 0 state. So this is psi 0, psi 0. So the initial state, if I think only of the initial state on the A system, it was this with all the out diagonal elements, right? We can call, so I'll just copy this to where we were. Let's go back to where we were. What was row A? It was just this, right? So this, we can call this our coefficient ij. And this here is corresponds exactly to the case of ii. So the action is exactly the same as in the discrete case, right? If you can do discrete, you can do continuous. This is for the special case where the pointer states don't overlap for different outcomes. But we saw that they can in principle overlap. So let's write here more general case. So we'll just see what it looks like. And then, like all difficult things, I'll let you do this in the tutorial. So let's say that the initial state of the pointer was maybe a more realistic Gaussian. Could be at least, oh, this is terrible. A more realistic Gaussian. Okay, which is kind of more fat. Which then, so this is say 0. And then you get here psi 1, which is still centered around TA1 and centered around TA2, for example, is, let's make it bigger. Okay, maybe something like this, right? So now there is some overlap between the two. Okay. So now we have that psi 1, psi 2, this is different from 0. Okay. So then we can ask still, so what is row A? So again, sorry, row A, no, oops, the map up to on row A. So this was what? It was this, where now we have some terms here. So when j is small, when j is different from I, so let's see, when I equals j, then phi j, phi I, this is going to be, sorry, I is going to be 1. But when I is different from j, then it's going to be something between 0 and 1 in absolute value. Okay, because it could also be a complex number. Which means what? Well, it means that this corresponds to cases where I and j are non-zero. So at the end of the day, we're going to still have here this C0, C0. Sorry. We're still going to end up here with this squared. We call it 1 and doesn't matter. So in the diagonal, we're still going to end up with all the squared elements. Okay. But now in the off diagonal, we still keep some terms that are not exactly 0. Which means that we don't get this perfect pinching, which means that the map on A is actually going to be a bit softer. This is why it's called a weak measurement. It's going to be a bit softer. It's not going to be as disruptive as before. It will not completely break the superposition. But this seems a bit hard to solve. So again, we found a problem that's a bit trickier. So we just think about what's the discrete equivalent. Okay. And this is what you'll do in the exercise class. The discrete equivalent for this psi I, psi j not being the delta function, which we can write here. Okay. And so let's think. So the case where, let's call it 0 and 1, this was 0, was the case we saw before, where we had, here we had our row A, and here we had started with state 0 on the pointer, right? And we applied a C naught. So if you look at it in the block sphere, if the state of A was 0, so you get this phi 0, which was 0. And when it was 1, you got this phi 1. That was precisely the state 1, okay? And what we're looking for is instead of doing this very abrupt rotation here that corresponds to an X gate, so remember the C naught was 0, 0 times the identity plus 1, 1 times X, right? So in this corresponding to if the resulted in that if the first system is in 0, then the second one really flips all the way down here. Okay? And these two states are not orthogonal in the sense that they don't have any overlap. Okay, so what we could do instead is instead of rotating it completely, rotate it just a little bit. So this gives us a different circuit. So this gives us a circuit where here we have a control gate, but it's a different type of control gate. I'll call it maybe. I'll write what's inside first. So we do a controlled rotation around the X gate by some angle theta, which means what? So this is going to be your phi 0, which is 0. But if the first qubit is 1, then the second qubit gets rotated by just psi 1, which is some rotation around theta of 0. Okay, so these two. Now, if you remember from the block sphere, if you have two states that have some angle between them, then the inner product between them is given by the cosine of this angle, right? So now we have our u being 0 times the identity plus 1 times a small rotation x of theta. Okay. two extreme cases. If theta is 0, then nothing happens, right? Then U is the identities, because then rotation x of 0 is nothing. Okay. If theta is, I think, pi, then you get rotation over x by pi being x. Okay, I'm not sure if it's pi because the angles were funny in that ball sphere, but I think that's right. Okay, so then you get the C naught. In this case, you get U being the identity. So in the former case, so this is when the two states like really overlap in the pointer, then it's like nothing happens. You'll see in the exercise class then what happens on the system A. It's just the identity. So it's the weakest measurement is so weak that nothing is happening. It's just the identity. On the other extreme, you have this case where you rotate so much that that like these two states are orthogonal. And then when you look at this map, it's really like you took a superposition to a mixture. But in between, this is where interesting things happen. Then you'll get states that have some overlap, and then you'll get a bit of off-diagonal terms over here. Okay, so in the tutorial, you'll see exactly how much depending on this value theta. Okay. We can talk about applications probably in a few lectures from now. But that's it. So today, we saw how we can apply channels to represent the local effect of measurements. Yep. And in the next lecture, we will follow up. No, we will continue with other parts of the lecture. Okay. Okay. So this is it. I think we had our extra half an hour. So thank you, and I'll see you, on Tuesday.